Okay, hello everybody. So we are going to be picking it back up, talking a little about nomenclature, and then moving into the second part of this chapter to talk about conformational analysis. So let's just quickly review some of the nomenclature rules that we went over last time by looking at a few examples. So what I like to do is to practice drawing going from the name to the structure. So you guys can try these out, and then, follow along with the video and see what you got. So let's say we wanted to draw out 3-isopropyl 2-methylhexane for starters. Okay, so to get going here, what you want to do is, again, pay attention to the parent name. So you have a hexane. So that means you're going to need a 6-carbon chain, okay, which I'm going to number arbitrarily 1, 2, 3, 4, 5, 6. Just make life easier for yourself. Since it's your structure, you can draw it however you want to. Just make for sure you put in everything in the correct position. So 3-isopropyl means that you're going to have an isopropyl group coming off of the number 3 position, and 2-methyl means you're going to have a methyl group coming off of 2 position. Okay, now let's try something else. Let's do something that's not a hydrocarbon. So let's say you have 3-methyl-1-butanol. Okay, so this is a butanol, so this is going to be a 4-carbon alcohol, all right? And you're going to have an alcohol at the number 1 position. So I'm going to start with that alcohol, the number 1 position, and then I'm going to draw 4-carbon chain out like this. And then 3-methyl means that I'm going to have a methyl group coming off of position number 3. Okay. All right. Now let's try something like this. So now we've got 4-ethyl 3,3-dimethyl 1-heptene. Okay, so heptene means that we have an alkene. So I'm going to start off with a carbon-carbon double bond, and then that's going to get the number 1 and number 2, okay, since it's the alkene is the highest priority functional group here, following the numbering. So 1, 2, then 3, then 4, then 5, then 6, then 7. And then for ethyl means we're going to have an ethyl group coming off of the number 4 position. You could draw it like pointing out like this to the side, or it can be drawn the other direction. Those are both equivalent because it's just a sigma bond rotation. And then 3,3-dimethyl means that you've got 2 methyl groups coming off of the number 3 position. Okay, then we've got one more. So let's say we want to do 6-ethyl 2,2-dimethyl cyclohexanol. Now notice cyclohexanol is not numbered, okay? And that's because the alcohol is understood to be the number 1 position. So what I'm going to do is I'm going to start off with it as my number 1. And then I'm going to number it. Now you can number it clockwise or counterclockwise. It doesn't matter in this case since you're installing the functional groups. So if you go and you put the 2 methyls here and you have a 6-ethyl here, that'll give you this structure. Now, just for fun, what I'm going to do is go ahead and show you what you would get if you had numbered it the other direction. Okay, so then you would have 2 methyl groups here at the number 2, and then at the number 6 you would have an ethyl group. Now, what I want you to notice is that these 2 structures are equivalent. Okay, the only thing that has happened here is I have simply turned the molecule over. Okay, now sometimes it's not that easy to do that because you have to pay attention to what's going on at certain positions in the ring system. But if there's no other indicator here, these are essentially equivalent structures, okay, the way that this is drawn. So this is one of the big challenges of this course, is to be able to recognize when you are looking at the same thing and when you are looking at something different. And that's kind of something that's going to be talked a lot about in the next chapter. Okay, so now we're going to get started with starting to talk about conformational analysis. And I have a lot of this written out already just because you know, you guys have the notes already, and so you can see it in front of you. So I figured this is just, I'll draw the structures out, and we'll go through that together. So what a conformer is it's a spatial arrangement of atoms as a result as a sigma bond rotation. Okay, so if you're looking at two conformers, we're essentially talking about two molecules that are the same thing, but the atoms are arranged differently based on rotating around a sigma bond. Now, one of the things that helps when you're doing this is to actually have a representation that allows you to look at a compound that has you know, three-dimensional orientation. So it kind of represents the true bond angle a little bit better. So here I've drawn out a molecule of ethane, okay, and obviously we know those are not 90 degrees, those should be 109.5. So what I'm going to do is I'm going to draw out those two carbons there for carbon 1 and carbon 2, and then I'm going to add in some perspective, okay, so I'm going to show, you know, one hydrogen is going to be coming out of the page towards us, and one hydrogen is going to be going into the page, so that now resembles a tetrahedral. Then I'm going to be doing the same thing over here with this carbon. Where one hydrogen is coming towards us out of the page, and then one is going back into the page, like so. All right. Now, even drawing it out this way, you know, we're studying about what's going wrong this sigma bond right here. There's another way that we can actually view this. And so this is something where I'm going to use what's called the mind's eye. So we're kind of, you know, viewing what we would see if we were looking down that bond right there. Okay. So the way we represent these is by doing what's called Newman projections. Okay. And so what a Newman projection is you look down the bond of interest using your mind's eye. And the first thing you want to do is draw a circle. Now that circle is going to be basically how we're going to be thinking about our substituents that are coming off of those carbons. Now, what you want to do is draw the substituents closest to the mind's eye, crossing into the circle that represents kind of their spatial arrangement. So you can see there's a hydrogen here that's coming out towards us. So I'm going to draw that hydrogen kind of going off to the right like this. And then there's another hydrogen over here on this side, okay, that's going away from us. Okay, so you can see if you kind of turn that around, you kind of have one hydrogen coming out, one hydrogen going in. And I just made that arbitrary assignment. And so the right-hand side is going to be coming out towards us, and the left-hand side will be going back into the page. But you could do it the other way, but that's just how I decided to do it, but you have to be consistent. And then one hydrogen is just straight down like so. So you can kind of see that this does kind of represent, you know, pretty close what the bond angle of interest here is. Now, as far as the other substituents, you want to draw the other substituents on the backside, touching the circle but not crossing into it. So in other words, the hydrogen atoms that are here, here, and here, this hydrogen atom is in between these two, which is those two hydrogen atoms. Okay, so this is hydrogen number 1, this is hydrogen number 1, this is hydrogen number 2, this is hydrogen number 2, and this is hydrogen number 3, and this is hydrogen number 3. Okay, well, I'm going to call this hydrogen A, and that is this hydrogen right here. So that's hydrogen A. Okay, it's in between 1 and 2. Okay, now in between hydrogen 2 and hydrogen 3, the hydrogen that's, you know, excuse me, shoot, back that up. There we go. Sorry about that, got ahead of myself. So hydrogen, hydrogen number 1 hydrogen coming out towards us. Hydrogen number 2 is the hydrogen that is going away from us, and that's hydrogen number 3. And so hydrogen A is between hydrogen number 1 and hydrogen number 2. I apologize for that. And so this is hydrogen number 2. This is hydrogen number 1. You got to be careful about this. This is hydrogen number 3. Okay. Now between hydrogen number 1 and hydrogen number 3, which is these two guys here, it's going to be that hydrogen that is also pointing towards us. So I'm going to call that B. And then between 2 and hydrogen 3 is going to be this hydrogen right here that's also going into the page. So I'm going to call that hydrogen C. Okay, so now you can get an idea as to where everybody is. And this looks horrible, so I apologize for that. I hate to not have this look good. So this is 1, this is 2, this is 3, this is 1, this is 2, this is 3. I feel bad because I had it right the first time, but I want to make for sure that it looks presentable. Okay, but I think you guys can see now kind of the spacing of all the hydrogen atoms there by doing this. And so this is a very useful way to represent molecules, and it's easy to kind of spin one of these groups either the forward or the back, and the carbons are actually in the plane, so you don't actually see them because you're looking at those groups head on, okay, those two carbon atoms, and you're just seeing the substituents that are around them. So again, the ones that are toward the front are the ones crossing, and the ones that are away are the ones that are just touching the circle. Okay, so now with all that being said, this group here, the way this is clearly drawn, you can see how all the groups are kind of spaced out apart from each other and that no group is on top of each other. Well, this is referred to as a staggered, okay? This is a staggered conformation. So that means that it spaces out all the atoms with maximum separation. And this is lower in energy. What you want to be thinking is that every hydrogen atom is associated with an electron that's being shared. And the closer that those are in close proximity, well, the greater repulsion there is between those electrons, okay? And so those are going to be higher energy states as those hydrogen atoms get closer together, okay? And eventually what will happen is the two groups will in fact be on top of each other, okay? And one group will overshadow the other one. And this will be a high energy state, which we refer to as eclipse, okay? So now what we're going to do is go ahead and consider that. So I've redrawn out that structure that we had just a moment ago. So here I've got the groups here that were in the front, okay, which was this was our 1, this was our 2, this was our 3, okay. And then we had our hydrogen atoms, you know, which was A, and then B, and then C. Now that's not going to be really relevant in a moment, but let me just show you. If you were to rotate this 60 degrees, okay, rotate the back 60 degrees. So we're rotating the black hydrogen atoms. Well, what's going to happen? Well, if you redraw the circle and you redraw in the original 3 groups, which did not move, what's happened now is that hydrogen A is now eclipsing hydrogen 1. Hydrogen B is now eclipsing hydrogen 3, and hydrogen C is eclipsing hydrogen 2. And so you can see that all of those hydrogen atoms are now, you know, in a high energy state. Now, if you were to continue to rotate this, well, then they're going to go out of eclipsing, and then they're going to go back into eclipsing. So you can kind of see that there's going to be some kind of, you know, sine wave interaction here where it's going up and down in energy, okay? So when we start off life here in this fully staggered, okay, conformation, this is going to be a relatively low energy conformation. And that energy is going to increase until you reach a maximum point at 60 degrees where all of the groups are eclipsing. Then you're going to continue to rotate, and they're going to go back to being in a staggered conformation, and then if you continue to rotate, it'll go back into an eclipsing conformation. Okay, and so if you were to graph out this, this particular diagram here, the energy, you're seeing the energy go up, and then come back down, and then go back up, and then come back down. And it would just keep doing that, okay? And the reason why it's a simple pattern like this is because, well, all the hydrogen atoms are equivalent, okay? So the next question is well, what would one of these look like if the molecule had different substituents, if it was not just hydrogen atoms that we were considering? Okay, so the next one that we're going to do is going to be a molecule of butane. Okay, so butane is 4 carbon, hydrocarbon, and I'm just going to go ahead and start off with its 3-dimensional picture. Okay, so we've got carbon, CH3 here, and a CH3 here, and I'm going to draw it in a staggered conformation. So we've got the 2 methyl groups like so. Then we're going to have 1 hydrogen atom coming out towards us, 1 hydrogen atom going away from us, 1 hydrogen atom coming out towards us, and 1 hydrogen atom going away from us. And what we're going to do is we're going to view this down the mind's eye, okay, like so. Now, I asked that you would look down carbon 2 and carbon 3. So if this is 1 and this is 2 and this is 3 and this is 4, that's what we're going to be viewing. So we want to represent what that looks like with a Newman projection. Okay, so you can try your hand at that now and pause the video and then see what the answer is. Okay, so you're going to start off with drawing a circle. All right, then you're going to have hydrogen atom that's coming out towards us, 1 hydrogen atom that's going away from us, and then a methyl group that is going straight down. Okay, then in between the 2 hydrogen atoms is this CH3 group, which you would draw just touching circle. Then you would have 1 hydrogen atom that would be pointing on the side where the hydrogen atom was drawn up, between that and the methyl group. And then the other hydrogen atom would be between the hydrogen atom that's drawn back and the methyl group, like so. Okay, now when you look at this, you can say, okay, well, this is clearly staggered, but there's something even kind of extra about this, and that is that notice the 2 largest groups, which are these methyl groups, are 180 degrees apart. They're as far apart as they can be. So those are called the bulkiest groups. So the bulkiest groups, which are your largest groups, are 180 degrees apart, and the molecule is staggered. Okay, when this occurs, this is basically a global minimum. That's going to be your lowest energy point that you have in this particular compound. Okay, this particular conformer is your lowest energy conformer. And this is what's referred to as the anti-conformer. All right, now if we were to go ahead and do some rotations here, okay, so let's do that. Now I'm going to do exactly what I did a moment ago with ethane, and I'm going to rotate the back 60 degrees, okay? And I'm going to draw out what that Newman projection looks like. Okay, so I've got my front all staying the same. Now my back groups, what I'm going to do is I'm going to go ahead and I'm going to draw those in blue so you can see those better. So I'm going to rotate all of those 60 degrees around. So that means what you're going to have is, well, there's going to be a CH3 group that's going to be eclipsing this hydrogen. Okay, there's going to be a hydrogen now that's going to be eclipsing that CH3. And there's going to be a hydrogen now that's going to be eclipsing this hydrogen. Okay, now again, everything there is eclipsed. Okay, and that's going to be a high energy point. Okay, now what I want to do is I want to take this structure here and I want to rotate that structure another 60 degrees. Okay, rotate the back 60 degrees. And I guess what we're doing is we're rotating clockwise, so let's just go ahead and say that we're doing that. So we're going to rotate the back 60 degrees clockwise. So let's draw out what that would look like. So again, your front groups remain unchanged. But now these groups in the back are all rotating 60 degrees. Okay, so that means now that methyl group is going to be, excuse me, there we go. That methyl group is going to be between the hydrogen and this CH3, so it's going to be right here. This hydrogen atom is going to be between the hydrogen and the CH3 on this side. And this hydrogen is going to be between the two hydrogen atoms at the top. Okay. Now, this is also a staggered conformation, but it is not as low as energy as the anti, because your bulkiest groups right here are now 60 degrees apart from each other, okay, and it's eclipsed. So this particular conformation is referred to as the gauche, okay, G-A-U-C-H-E. And what that essentially means is that the bulkiest groups are 60 degrees apart, and this is staggered. Okay, so the gauche is going to be lower in energy than that eclipsed conformation, but it's not going to be as low as energy as the anti. Okay, now if we go ahead and we do one more rotation of this, so that now this hydrogen is going to move over here, that methyl group is going to move right here, and that hydrogen atom is going to move up there. So we're going to redraw our groups in the front. And now what you're going to have is you're going to have a hydrogen atom that's eclipsing this hydrogen atom. You're going to have a methyl group that's eclipsing that methyl group. And you're going to have a hydrogen atom that's eclipsing that hydrogen atom. And so this is eclipsed, but this particular eclipsed is going to be the highest in energy. Now there's no special name that I'm aware of for that, but what you want to recognize is that this eclipsed is higher in energy than this one. Now why do you think that is the case? And if you said, well, it's due to sterics, you're exactly right. The two bulkiest groups here are on top of each other, and so there's a lot more sterics, or what we call static repulsion, between those groups. Now what I want to do is I want to try to graph what we've just done in a 360-degree rotation, where we're rotating that back group 60 degrees each time. So we're going to start off at 0, and 0 was the anti-conformation, and so that means that this is starting off life right here. Okay, then this is going to climb in energy until we get to this eclipsed conformation at 60 degrees. Okay, and then we're going to rotate again And we're going to go back down in energy, but we're not going to go down as energy as far as the anti, and that's where we're going to have our gauche conformation. And then we're going to rotate again, and now we're going to be even higher in energy than this conformation to get to this point right here, which should be your highest point. Now, since everything else is symmetrical, you can pretty much just line it up from here, okay? If you rotate this another 60 degrees, you're obviously going to be back at that gauche conformation again, where the two bulkiest groups are 60 degrees apart. And then if you keep rotating, it's going to be back to the equivalent eclipsed conformation that we had earlier, which was up here, as you're going to have now the hydrogens are going to be eclipsing the methyl groups rather than the methyl groups eclipsing each other. And then if you keep rotating all the way to a full 360, you should go back to the original anti. Okay? Now filling that in, that's going to give you a energy diagram. That's going to look something like that. Okay? So you can see there are some differences in these diagrams, of course, and depending on what the substituents are that you have present. Okay? Now, one of the big exercises for this chapter is being able to look at these kinds of graphs and determine, okay, whether you're an eclipsed or an anti or a gauche conformation, and then being able to draw out different conformations of molecules and verifying whether you're looking at two conformers or if you're looking at two completely different molecules. So there's a lot of questions that are in the homework, in the book and in sampling that kind of go over this. So you want to definitely kind of make for sure that you pay attention to those things. Okay, now I think what I'm going to go ahead and do is I'm just going to move into the next topic of conformers, since this is all kind of related, which deals with the conformation of cyclic systems, okay? And so we're going to start off by talking about small rings. Okay, so small rings, rings that are 3 or 4-membered rings, are high in energy. They are high in energy. And this is due to a phenomenon that's known as ring strain. Okay? Now, if you were to go and draw a structure of cyclopropane, that looks something like this. Okay, the bond angle for cyclopropane is roughly about 60 degrees, okay? Now, this carbon atom right here, however, is attached to 4 different groups. So that means in reality, that bond angle should be closer to 109.5. But it has a 60-degree bond angle, which means you have a 49.5 degree amount of ring strain that's associated with that system. Okay. Likewise, when you look at systems like cyclobutane, has a bond angle that's close to about 90 degrees. And if you were to look at its ring strain, it would be closer to that, about 19.5. So the cyclobutane has a little bit less ring strain than the cyclopropane, but it's still not great. Now, one of the things I'm going to mention about all of these systems is that I'm drawing them out planar, but in reality, if you were to make a model of this particular molecule right here, you would find that everything is kind of bowed, okay, like with the 3 atoms, like it's kind of bowed out. And so there is definitely some deviation from the 60 and 90 degree. This is particularly true when you try to make a 4-membered ring. You're going to see that how it naturally kind of wants to go is kind of in a folded manner, so that you have kind of like this this bend in the system, where it's trying to get a bond angle that's a little bit, the bond angle can actually be contorted a little bit to about 88 degrees, just because of how the atoms are held together, which is, giving it a little bit, technically a little bit more ring strain, but it kind of helps how the atoms sit so that the hydrogen atoms are not quite in such a bad state. Now, both of these systems can be synthesized. You can make them, but and there's a lot of chemistry that's been done with them. But the real focus of looking at different kinds of conformers really comes in looking at 5- and 6-membered rings. And so 5-membered rings like a cyclopentane, have much less ring strain. And that's just because of how the atoms are situated. So if you were to look at, let's say, cyclopentane, something like this, in reality, cyclopentane actually kind of sits in a structure that looks kind of like this, okay, where it's got a little bit of a bend in it. And so because of this, it gets a bond angle that's, kind of close to 109.5, so a lot less ring strain associated with it. Now, where there has been a lot of study and where there's been a lot of thought given into this is really coming from 6-membered rings, particularly cyclohexane, have virtually no ring strain. And the reason is because this molecule does not have to sit planar at all. So if you were going to draw something like this and say, okay, this is how we typically represent cyclohexane when we're drawing it quickly. But in reality, the actual structure itself sits a little bit differently. So the way that you generally draw these is you start off and you draw 2 parallel lines. Draw 2 parallel lines, slightly spaced apart. Okay, so I'm going to start off by drawing 2 parallel lines that are slightly kind of spaced apart, like so. Okay, and then 2 connect 2 lines at the end about 109.5 degrees. Now, obviously, it's not going to be perfect, so you're going to kind of estimate it. So, all right, so I'm going to put 1 here, like so, and I'm going to put 1 here, like so, okay? And then 3, connect the ends. So that you have these 2 ends connected here, and these 2 ends connected there. Okay, and this is more to how the molecule actually sits. Okay, now in a system like this, there are obviously hydrogen atoms that are sitting kind of all over this system, and this is what's referred to as a chair conformer. Okay, I'm going to redraw that, and I'm going to try to draw it a little bit better by drawing a little bit faster. Okay, and what I'm going to do is I'm going to show where all the hydrogen atoms are. Okay, now every carbon has 2 hydrogen atoms associated with it. So some hydrogen atoms are going to be pointing up like this, and we refer to those hydrogens as axial. And it turns out that every position is going to have an axial hydrogen in a chair structure. So over here at this one, notice there's going to be a hydrogen atom here that's also going to be axial. Okay, so that means over here there's going to be a hydrogen atom that's going to be axial. Now it's very important that you see how they're alternating, like one is pointing up, one is pointing down, one is pointing up. Pay attention to that. That's going to be a useful tool in a minute. Okay, then over here, hydrogen axial. then over here, hydrogen axial, and then right here, hydrogen axial. Okay, so there are all of our axial hydrogens. Now, the other hydrogen is pointing out, okay, and kind of away from the structure in an equatorial plane. So those hydrogen atoms are referred to as equatorial. Okay, and just like there was an axial hydrogen in every position, there's an equatorial hydrogen. So see how this hydrogen here is technically pointed down? Well, then this equatorial hydrogen will be pointing up relative to that one. Then over here, where I've got one axial hydrogen pointing up, there's going to be an equatorial hydrogen that's going to be pointing down. Then over here, there's an axial hydrogen that's pointing down, and there's going to be a hydrogen atom that's going to be equatorial pointing up. Over here, axial hydrogen pointing up, equatorial hydrogen pointing down. Over here, axial hydrogen pointing down. Over here, equatorial hydrogen pointing up. Okay? Now, if I were to go through and number all of those carbons, so that this is carbon number 1, 2, 3, 4, 5, and 6. And if I were to bring the top of this chair, like imagine this is kind of like a chair at the beach, okay, where you can fold the foot and the head of that chair and invert it. So let's say I make the head of the chair go down, and I bring the foot of the chair up, so that this is now an inverted chair. And so this is called a chair inversion. Okay. Well, if you were to do that, okay, well then now what's going to happen is that trying to keep that same kind of orientation going, is that I've now got this is my number 1 position, but this over here is now my number 4 position, because I moved it up, I moved that one down. So this is number 2, this is number 3, it's number 5, and that's number 6. Now, there are still obviously all those hydrogen atoms there. But what happens when you do this is that the hydrogen atom that was red, okay, that was drawn equatorial, well, when you do this chair inversion, well, now that hydrogen atom is going to be pointing down, but it's going to be axial, okay? And this hydrogen atom that was axial, well, it's still going to be pointing up, but it's going to be equatorial, okay? Now, likewise, if you come over here to 4, you see the same thing that happened over there. That axial hydrogen that's pointing down is now going to be an equatorial hydrogen that's pointing down. And that equatorial hydrogen that was pointing up relative to that axial one is now going to be a hydrogen atom that's going to be pointing axial. So what does this mean? What this means is whenever you do a chair inversion, all axial groups become equatorial. And all equatorial become axial. Now their positions are still the same. Like if we're using the term up and down, that's still there, okay? What's changed is, well, one is now axial, one is now equatorial. And so that's kind of important to keep that in your mind as we kind of start to look at some more complicated chair systems. Now, this, by the way, is definitely a skill that you get better at, okay, the more that you practice it, okay? Now, if we were going to branch out to a little bit more complicated system, okay, and we wanted to look at, let's say, a molecule of methyl cyclohexane. All right, well, there's some ways that I could draw that methyl group right there. And I'm going to start off by drawing it so that the methyl group here is oriented like so. Okay, so that's pointing up. Now, one of the things I want you to notice is if I count over 1, 2, 3, okay, 4, 5, 6, like that. And I look at this hydrogen atom here and this hydrogen atom here. Those hydrogen atoms are interacting with that CH3, and that is a steric repulsion, okay? And this is what's called a diaxial strain, okay? And it's one of the main reasons why large groups prefer to be equatorial, okay? So if I were to take this structure, okay, and start to do some contortions on it. So let's say I only bring the foot up, okay, and I leave the head up on this side. Well, what that's going to give me is a structure that looks like this, okay? And so now my CH3 group, which is right here, there's now going to be a hydrogen atom here that's on position number 4 that's going to be interacting with that. Okay, and these are in very close proximity. Okay, this particular conformation is called the boat. Okay. Oh, okay. The power just went out for a minute. I hope this is still recording. So this sterical interaction right here, if you would imagine that there's like, I put like a little mast here and a flag, okay, this is what's called the flagpole interaction. And the flagpole interaction is very high sterics, and one of the main reasons why boat conformations are generally not low in energy. Now, if I were to continue to bring that, let's say that foot, okay, now bring it down so that we do a true chair inversion. Like so. Well, now what's happened is, again, this is now position number 1, okay? And the way that that methyl group is going to be drawn is going to be drawn out like this, okay? And here it's clearly equatorial. And so now this group has less sterics because of it, okay? So the bulkiest group will prefer or to be equatorial in the lowest energy conformation, okay? Because there is just less sterics here. You don't have this diaxial interaction that you were seeing a moment ago. And this should feel very familiar to you coming right off of the discussion about talking about acyclic systems and looking at those types of conformers, okay? Now, one of the things that we can do is, you know, this little rule here is kind of a beacon, but you want to be careful about how you apply it. So this is only true for the lowest energy conformer, and it doesn't mean that there are other conformers don't exist. Like the boat exists, and there's a whole bunch that I'm skipping here. Like if you look in the textbook, there's this thing called the twist boat and the half boat and all that business. Well, there's a conformer name for all of those, and I don't want us to get into all of that. If you know just chair and boat, that's fine. What I want you to be focused on, though, is to recognize that just like what we were seeing a moment ago with these kind of energy profiles, with butane, you also have that with cyclohexane. Now, something I didn't ask is well, which of these conformers do you think the molecule you would find in probability-wise most of the time? And if you said anti, well, that's correct, because if you dropped a whole bunch of balls into this, okay, most of them are going to land in the valleys, okay? And so that means you're generally going to find things that are going to be in eclipsed conformations, which in cyclohexane generally means chair conformations, okay? And so those are generally the preferred conformations that you see in systems. So there's always anomalies out there, but that's just something I want to kind of point out. Now, one of the things that students often have trouble with is visualizing how groups are oriented and how you should represent those in a particular molecule. So let's say that we had something like this trans 1,2-dimethyl cyclohexane, okay? And you wanted to draw out, draw the conformer of lowest energy. Okay. Well, you're going to start off with a chair, and it could be either way. I'm just going to draw this particular chair, and I'm going to call this number 1 and this number 2. This number 1 and this number 2. Now, this is where students have trouble. You may think that the best way to draw these is to have both of those methyl groups out. And that's correct, okay? You would have this methyl group here shooting out to be equatorial. But the reason why that the second one is equatorial has really has nothing to do with with the fact that you want them to both be equatorial. It has to do with the stereochemistry. All right, and I'm looking at this now, and I've decided I'm going to change my numbering. So I know I've done this twice, but forgive me here. I want to follow through with this example. So if this is number 1, notice how there's 2 positions here for number 1. And notice the methyl group here is drawn down relative to that hydrogen. Now, if this is going to be trans, then that means one group is pointing down, the other group needs to be pointing up. So the reason why on number 2 that the CH3 group is equatorial is not because that it wants to be equatorial, it's that it has to be drawn that way because that would be the position where that methyl group is pointing up. So the way that you generally do these is you have to find one bulky group and use it to dictate the stereochemistry of everything else. And if they're the equivalent, like they are in this case, then you just pick one of them arbitrarily and then draw everything else around it based on the stereochemistry, not based on whether it's axial-equatorial. Only the first group is the one that you would need to consider axial-equatorial. Okay, so what do you think about cis 1,2-dimethyl cyclohexane? What do you think its most stable conformer would look like? Well, it would look something like this. Now, again, the reason why I picked those positions the way that I did is I wanted this methyl group here to be pointing up and for it to be equatorial, and it is. So that means all the other groups around it now have to follow its stereochemistry. So that means that, okay, if this is going to be equatorial, well, then that group has to be axial. Okay, now let's say you don't want to draw all this out every single time. Like you want to try to figure this out relatively quickly. How will you do that? Well, if you remember a moment ago where we were doing this diagram about axial, equatorial, notice how they alternate, okay? Like you've got an axial up, an axial down, axial up, axial down. Same thing with equatorial. Equatorial you have down, equatorial you have up. Equatorial you have down, equatorial you have up. So that means that all the positions, if they're pointing in the same direction, well, then that means that those should alternate, okay? Meaning if you went in and penciled in the rest of the hydrogen atoms here, so that everything was all pointing up, and you said that one of these groups is equatorial, well, then by default, that methyl group would have to be axial in the lowest energy conformation. Likewise, that hydrogen atom right there that's drawn up would now be equatorial. That hydrogen atom would be axial. This hydrogen atom would be equatorial. That hydrogen atom would be axial. So it alternates like that, okay? So if you pay attention to the direction that the bulkiest group is pointing, you can then assign where all the other groups are going to be pointing without having to draw the chair structure. This is a real big time saver, especially on an exam, okay? So let's say that we want to draw the most stable conformer of the following molecule, okay? All right. So I've got an isopropyl group here, and I've got a methyl group here, and a methyl group here, okay? All right, so now, how would you go about doing this? All right, so first thing I'm going to do is I'm going to draw a chair structure. Now, before you start numbering anything, ask yourself a question. You know this is the bulkiest group, so you would like it to be equatorial. So could you pick a position on the chair right now that would be up and equatorial? Now, if you went here, which is where most people's eyes go to, you draw it up, well, that's axial. But if you go here, you draw it up, well, that's equatorial. Well, that's exactly what we want, okay? So that means that now counting over, okay, so we're going to count over now. So we've got number 1, number 2, number 3, number 4, number 5, number 6. So this is number 1, number 2, number 3, number 4. So I need to draw number 4 down relative to that group. So there's two options here. One hydrogen, one going up, one going down. I want the one going down. So that's where I want that CH3 group to go, which I'm going to put in purple so we can see that. And now going over to 5, which is right here, I have another CH3 group, but it's pointing down. So 5, you can either go down or you can go up. Well, we need to go down. So I know that that group needs to be axial. And that one is equatorial. Now, you could have made those predictions without having to draw this whole thing out. If the question is to draw it out, well, that's what it would look like. But if you're trying to predict whether those are axial, equatorial, you can just do the trick I did just a moment ago. So for instance, okay, you draw these hydrogen atoms in here, and here, and here, and here, and here, and just all the ones that are pointing in the same direction as your bulkiest group. Say, okay, that is equatorial, well then this hydrogen here has to be axial. Well, that hydrogen has to be equatorial. So that hydrogen has to be axial. So if that hydrogen axial, by default, that right there is equatorial. And if that hydrogen is axial, then this hydrogen up here has to be equatorial, which means that methyl group has to be axial. It's a big time saver to be able to do that. Okay, so that that is a very, very useful, very useful tool. It does take a little bit of time to get used to that, but once you kind of get comfortable with that whole process, it really starts to make sense. Okay, I'm going to do one more. I know this is a very long lecture, but I wanted to kind of get this all out in one go. So let's say we had a chlorine group here, and an isopropyl group here. And so the question here now is a little bit different. So this question is determine if any hydrogen atoms are axial on adjacent carbons next to the axial chlorine. Now, this question is telling you that the chlorine is axial. So it's dictating that much to you. So it's asking on adjacent carbons, that means this carbon here and this carbon here, if there are any other hydrogen atoms that are axial, okay? Now, obviously, on the carbon right here, on the left side, one hydrogen atom is going up and one hydrogen atom is going back. So that means that if this chlorine here is axial, it's pointing up, well, then that hydrogen that's pointing up is equatorial, and the one that's pointing back is axial. So there's one, okay? Now over on this side, you can see where that isopropyl group is drawn, but what's not drawn in is the hydrogen atom. So anytime you see one group pointing in a specific direction, the hydrogen atom is going to be pointing in the other direction. So that means if there's an isopropyl group that's drawn back, there's a hydrogen atom that's drawn up at this position, okay? So now making that determination, if that chlorine group, again, that's pointing up is axial, well, that hydrogen atom that's pointing up is going to be equatorial. So this hydrogen atom right here is not axial, okay? It's equatorial, so it's only that one right there. Now that may sound like a pointless exercise, but when we get later on to chapter 7, you're going to be doing that activity to determine which hydrogen atoms can actually be eliminated to force the formation of an alkene, okay? So this tool, being able to do this, is very useful in predicting viability of reactions. Okay, so that gets me through everything what I wanted to say about conformational analysis, talking about chairs, talking about Newman projections. And what I'm going to do is I'm going to have a third lecture that's going to be devoted to chemical reactions. This isn't really something that I did in the notes, but I decided I wanted to go ahead and do this topic now as it kind of relates to what we've been discussing in the chapter. So I'm going to have one more lecture on chapter 4, and then we're going to be moving into chapter 5. Okay, so that's it for today, guys. I hope everybody's doing okay. And again, if you have any questions or comments, please leave them in video or send me an email, and I will get back with you as soon as I can. Okay, everybody take care. I will talk to you guys again. See you in the next video. Bye-bye.